SwayamPrabha. Digital India. Educated India.
So, clearly we initially figured out that such waves are called planar wave fronts, is not it. So, now when you have kx and ky to be 0, they are not trivial solutions, they might be trivial for that equations, but when we put kx and ky each to be 0, we will get planar wave fronts. That is, there is no variation along the x and y direction. The only variation in the pressure values that can happen is when the wave propagates from one z distance, say z1, it moves from z1 to z2. The variation is only along the upstream or the downstream direction. There is no variation along the cross section of the rectangular duct. That is, if you have I just drew the cross section of the duct a while back. So, along the cross section the pressure remains constant for the case kx is equal to ky is equal to 0, or when m is equal to n is equal to 0. So, anyhow, what is obviously important is that we have to substitute kx square and ky square, and also assume, well, insist that that is what we do, that this guy is minus k z square. We will keep this thing here, and what we will do, so what we will do, we will put this minus kz thing and one multiply, carry about our regular business of multiplying this, and remember we are getting a term k naught square here, this is 0, and then there is another term which is your relative to damping. So, this is to minus 2 j k m naught k naught, and this is minus k z. So, minus minus is plus, so plus 2 j k m naught k naught into k z. This entire thing is then like this. Now, let us consider the case of 0 mean flow. Let us consider quickly the case of 0 mean flow. When you have your m naught is 0, we are introducing for the first time the concept of cut on frequencies or cut off frequency. So, when you have such a thing, then clearly k naught square is equal to kx square plus ky square plus kz square. So, what is this cut on frequency? We will soon figure out in different context. So, we can write your k z as root over plus minus, of course, like this, all right. The guy under the bracket, that is, well, you can consider this like this. So, when clearly this kx square plus ky square, the sum of these, sum of the squares, if that is greater than k naught, or in other words, when k naught is less than k naught square is less than kx square plus ky square, then the term under the bracket is negative. That would mean you have, what does it mean? It means kz is your is purely imaginary. Okay. So, that would mean, remember now kz is multiplied by I times kz, that is what, that is what it will happen. Once you insist this kind of a variation where I am pointing and try to put on your kx ky value and try to solve for, try to figure out what is kz. Basically, once you figure out your kx ky in terms of the boundary condition and substitute that, and then try to solve for your z dash by z, or z field variation along the z direction, and for that you must come to the step of assuming this kind of a variation, what I am presenting here, and then when you need to solve for kz. So, we will see that if kz is purely imaginary, then it is then the solutions are either spatially growing or exponentially decaying. So, basically such waves are called the solutions which decay exponentially in space. Such waves are called evanescent waves. In our case, what will happen for a rigid wall waveguide, what will happen is that kz will be equal to This is of course the case without any mean flow. So, let me just put it n pi by, I guess it was b, and m pi by h. Okay. We get this kz is equal to plus minus root over like this, we get this. So, now we would get this kind of a solution if k naught is greater than or equal to root over n pi by b whole square plus m pi by h square, then that m n mode will propagate. If it is less, then it does not. Now, let us revisit the discussion when we just having where m is equal to n, where your m is equal to n is equal to 0. So, what do we get under such a situation? We will get k naught is always greater than 0. So, whatever k naught, remember this is nothing but omega by c, omega is 2 pi f by c naught. So, for whatever frequency of excitation you have, for a rigid walled rectangular waveguide, rigid walled rectangular waveguide, whatever frequency of excitation is there, the first mode is the plane wave mode, which always propagates. By definition, it is called plane wave because there is no variation along the rectangular cross section, what we discussed a while back. So, basically your 0 mode, that is a plane wave mode, that is the lowest mode and will always propagate. Now, depending upon the geometry, typically we consider B is equal to H, that is a square waveguide, that is waveguide with a square cross section, so that things become easier to analyze, although it need not be square. So, then we can figure out what is the first mode to get started or to be propagated. So, now we got this kind of a solution or the expression for the cut-on frequency. To summarize this particular concept of cut-on frequencies, we will have a wave number and m this particular m n mode, which is nothing but, let us say C m n is associated, I just had written it, y by h, you have this. So, now this mode will propagate if your k naught is greater than this thing cut on that. So, in such a case this mnth mode will be cut on, or it will no longer be evanescent. If k naught is less than this value, then such waves are called evanescent waves, they decay spatially. You have two solutions, e to the power something like minus mx or a minus mz plus e to the power plus some other constant times e to the power mz. The part which is decaying exponentially, that is called evanescent parts, and so that will not propagate. So, that is what is going to happen. What we need to do basically now is derive the full modal solution. Let us for simplicity assume that mean flow is not there, that is a stationary medium is there. So, what will we get? We need to sort of go back to our this guy. When the mean flow is not there, of course, this term goes away and you simply do not have this term, you just have one, and then we get our regular stuff, and that we can substitute in this equation. Okay. And the solution for this particular equation is simple, and we can hope to solve this by assuming a certain thing. So, we have your z this thing plus k z square times z is equal to 0. So, z will become your a1 times e to the power minus k z plus a2 times e to the power j, this is j times k z. Okay. We will have this kind of a thing where k z is given by the expressions that were noted above. So, under such a situation, if we go back to our definition or variable separate form, which is your this, and of course, I am not writing the time factor, it is assumed that it is time harmonic we are going to get. Let us say we are taking the Cmn constant inside. So, under such a situation we will be getting our complete modal solution, which will be of the form, let me call this C1 instead of, well, when we write it finally, which is your m is 0 to infinity and n is 0 to infinity. So, cos of m pi x by b into cos of n pi y by h whole thing, and here you have C1 mn e to the power minus j k z mn plus C2 mn times e to the power j k z mn. Okay. So, this is your finally the solution that we get, the modal solution, the much sought after solution that we were working so hard to get, the solution that is for rectangular infinite rectangular waveguide. Z is this direction, x is here, y is here. So, clearly when you have a pressure variation given by the encircled term, so that means high order modes, and we have this wave front that propagates along the positive direction, one that propagates along the negative direction. Again derive cut on frequencies in terms of the corresponding wave numbers. So, we just saw that k naught square, when this is greater than m pi by b and n pi by h whole square thing, it will be mode will be propagated unattenuated, that is the waves will not be cut off, it will be cut on. So, remember we can write this thing as 2 pi f by C naught, and this is greater than this value, is not it? What is C naught by f? C naught by f is your wavelength. So, here we are getting this in the denominator, and remember we can take the pi, we can take pi common and get m by b whole square plus n by h whole square. So, these guys will get cancelled, and we will eventually get the following relation. That means, if the excitation wavelength is less than this value, then that particular mode, Mn mode, will propagate. This is yet another alternate statement. The reason that I am emphasizing this multiple times is because this is central to our, when we will do the 3D analysis of mufflers, we will see that although we have infinite solution, but it is not necessary to consider all the infinite terms. Had that been the case, it will be practically impossible to do it. So, we need to worry only about the first few modes, in particular only those modes will propagate. So, at low frequencies only the planar wave is important, nothing else is important. Of course, the first few evanescent modes, if we consider that, our solution accuracy might improve for some muffler configurations at low frequencies, but only beyond the cut on frequencies we may beyond the first cut on frequency we may have to consider modes other than the planar wave mode. So, the idea behind considering this thing is that only the first few terms in the modal solution is important, it is not necessary to consider all the terms. Okay. So, that is of great importance here. So, that is the case. Now, clearly we can also derive there is another concept that needs to be done, that is the volume velocity concept. For that we have to understand the velocity along the z directions, but before that let me present to you figure which shows you the modal distribution or the mode shapes of a rigid walled rectangular waveguide. So, clearly this is your plane wave mode, this is your plane wave. Plus means that across this rectangular cross section, as we promised, this is your B and this is your height. Okay. So, across this cross section you have your acoustic quantity to be constant. Now, when you go for a modal m, well, m is equal to 1, but n is 0. So, you get the acoustic pressure is, the region is divided into two halves of equal of which are in opposite phase. So, this is given by your function cos of cos of m is 1 here. So, 1 pi by x by b. At x is equal to 0, you are getting whatever you are getting, and as we go along the duct x is equal to, when it is b, then it is minus 1 here. So, there will be some transition point at x is equal to b by 2, that is half the distance, where this is 0. So, this is your nodes. So, what is important here is the nodal pattern, that is the dotted line you see, that is a line where exactly the pressure is identically 0. So, basically that line divides the rectangular cross section into two halves of opposite phases. So, at all times they will be, so if you consider the point here and immediate point here, they will be exactly in opposite phase. As we go for higher solutions, if you consider 2 here, that is your this particular solution, and measure things from here. So, basically then gradually the phase is shifting from plus to negative and again going back. So, you have two nodal lines. So, it divides the rectangular cross section into regions of alternating phase from plus to minus, minus to back to plus. So, these are called modes along the x direction. Similarly, you have modes along the y direction, opposite phase along the y direction, and more. Then these modes, all these set in you can arrange this in a matrix. So, if you go along this direction, these are modes along the y direction, but there is no variation along the x. Similarly, here you have variation along the x, but no variation along the y. And these modes are all cross modes, where there is simultaneous variation of acoustic pressure along the x and y direction both. So, this obviously comes out very nicely from applying the boundary conditions as we saw, and they are nothing but plots of the trigonometric functions. So, this is sort of a very classical solution, very well known. So, now what we probably can do is have a look at the solution when we have mean flow, but before that it is good to also talk about your velocity along the z direction, which is, this is important when we basically get ourselves a little familiar with 3-dimensional approaches like your piston driven approach or things like that. So, from the Euler equations we can easily show, I am not going into the details, that u z m n, the particle velocity for the mnth mode along the z direction, is given by this variation, and when we simplify stuff we will get your this kind of a thing. So, C1 into C1 m n into e to the power minus j whatever it happens, and plus C2 m n into e to the power j whatever is there, and cos of some variation, and then you also have your cos of another variation and e j omega t. Now, what is important is that along a given, if you fix z is equal to some value, and if we now want to find out the volume velocity or mass velocity. So, that is nothing but if we integrate, as we saw from our last first couple of lectures and also the last few lectures of week 1, we defined mass velocity as rho times u, cross section area, into u. So, in this case it is u m n, but then this s this was the case when u was constant, but what do we do for the case when your u z m n is varying? So, obviously we need to integrate over the cross section, where ds is the rectangular cross section as we discussed. So, if we were to do it, so dx is nothing but dx dy, isn't it, dx dy. So, since it is going from the full thing 0 to b, 0 to h, what we can do is cos of m pi x by b dx 0 to b So, it is rather trivial to show that these quantities will be 0 when m is not equal to 0 and n is not equal to 0. So, that is for all, even if one quantity is non-zero, we will have these integrals to be 0. It is pretty fairly straightforward to do the integration and verify for ourselves, but in case it is m is 0 and n is 0, we will just get dx and dy. So, basically we are going to get b by h, we are just going to get that. When what this really means, that is, this is if either is important, that basically the contribution in the mass velocity by the higher order modes m n mode is identically 0. That is, higher order modes, if you integrate the velocity contribution by them over the cross section area, that is going to be 0, and this you will see, we can show that eventually in our discussions in the later weeks of our course, that this is probably one of the reasons why a plane wave is a very good approximation. That is, when we assume at a certain area discontinuity, which we are probably going to see in the week 5 and week 6, we are going to see, we are going to insist that volume mass velocity is constant across the certain area discontinuity. So, all these things will be sort of useful, at least for a cylindrical rectangular waveguide, and same discussion can also happen for a valid for a cylindrical waveguide. Now, let us quickly write down the solution for the case when you have non-zero mean flow, m naught is there, and then we will sort of end our discussion for the rectangular waveguide. So, your kz mn mode plus minus, plus is now basically the wave number or the wave component that goes along the positive z direction, and negative for this one. This is given a minus plus m naught into k naught plus square root of k naught square minus 1 minus m naught square, and your m pi b this thing, and here in the denominator you will have this kind of a thing. So, clearly when m naught is 0, we can get back our familiar expression. We can see this term will not be there, this term will be obviously 0, and this will be just be unity. So, you will get back our original stuff. Now, if that is not the case, let us analyze. So, what basically does that mean flow, when you have a mean flow m naught, this will, the effect of mean flow is to basically lower the cut on frequency. So, clearly when you have k naught square, if it is greater than, or probably we can write it like this, 1 minus m naught square and root over this square plus this square. When this is the case, then mnth mode will propagate in the presence of a mean flow. So, we can sort of do the algebra and figure out that when lambda should be greater than 2, and there will be your factor of root over 1 minus m naught square, and in the on the numerator you will have your sum square plus sum square, which is your y b by h m and something like that, and frequency can also be figured out using that. And this solution then can be put in the modal solution thing to get us the final thing, but basically the modal solution then will sort of look like, it will be very similar to your case when you have 0 mean flow, and so here you have your cos of m pi x by b to cos of n pi y by h into C1 mn into e to the power minus, now this something has to be paid attention to, this is plus. So, this is your positive propagating part into z plus C2 times e to the power j minus k mn z, okay, and this is your e j omega t. Okay. So, this is what we are going to get, this is what it is, and then how we figured out that solution of kz, I leave it as an exercise to the students here, and shortly we are also now going to, now remember these lectures are combined, the lectures 3 to 5 in the week 2 are combined and we are going to have a massive thing. So, shortly now we are going to have the discussion on cylindrical waveguides. So, for that we need to understand it's involved, it's fairly more mathematically involved, and we need to, what we probably do is that directly get on with the conversion of Laplacian into the cylindrical polar coordinates, and then get to the variable separation form, and probably not get into the derivation of the Bessel function, which is invariably comes up when you deal with circular cylindrical geometries in almost all physical problems, and then our solutions will proceed and things will become very interesting, because then most of our mufflers are circular in shapes in cross section. So, it is important to understand that. Of course, there are some variations also. Let us start the circular or circular cylindrical waveguide. So, what do we need to do now? So, circular cylindrical waveguides. So, it is basically, instead of a rectangular cross section, we have a circular cross section. So, what is the motivation of doing this? So, because most of the silencers or mufflers, they are of circular cross sections, like I mentioned a while back. So, this is your muffler cross section, all right, and this is the direction that is extending. Okay. Now, the thing is, we need to first introduce some transformation. Remember, our Laplacian in the regular Cartesian system was given by this thing. Now, in order to get to the case of circular cylindrical waveguides, what we need to do we have this kind of a thing. We introduce this transformation. Z is this direction, which is the same, and this is your r direction, and this is your theta direction. So, x and y are related to r and theta by the relations that are presented here on the top. So, using this, using our Jacobian matrices, and basically using the conventional rules of partial derivatives, that is, if you want to do this, this can be written something like this plus your theta times x. So, from the previous relations, like if you go up, we will see del x by del r or del r by del x. We can figure out from that relation, basically it is nothing but r square is equal to x square plus y square. So, you will get 2r is equal to 2x, and here of course you will have this. So, 2 will go away, and del r by del x will be x by r. X by r is nothing but cos theta. In a similar manner, what we are going to get here, this will be sin theta. Okay. So, this is what we are going to get. And if we do the same thing for the y variable, we are probably going to get here probably there will be a minus sign here, and here will probably have your sin theta. This will probably be your cos theta, something like that. Not very sure of the symbols here regarding the signs, but you can verify. The thing is that we would like to figure out what is this and what is this in terms of the partial derivatives of with respect to r and with respect to theta. Of course, there might be terms which multiply, there might be terms involving r or theta that multiply to the partial derivatives like this, but after some algebra we can readily show that your Laplacian, the cylindrical polar coordinates, basically your this will become so this is your Laplacian in cylindrical polar coordinates. So, if you were to get rid of this term, you will just have polar coordinates or circular polar coordinates, but we have our 3D case. So, we will have to retain z term as well. Now, what do we do with this thing? So, basically the idea is we remember our Helmholtz equation. Our Helmholtz equation was nothing but del square plus k naught square operating upon p tilde is 0. That would mean this is p tilde plus 1 by r del r p tilde 1 by r square operates upon this p tilde is 0. So, this is your wave equation in cylindrical polar coordinates. Obviously, there is a lot of work to be done before you arrive here. So, I am just presenting the final product, what is going to happen. Cylindrical polar coordinates also allows for the separation of variables. So, what it means is that we can probably write this as something like r of r, theta of theta and z of z. So, this guy is our original thing. Let us for simplicity consider only the case of stationary medium, cylindrical duct, circular cylindrical duct with a stationary medium, that is m naught is 0, Mach number is 0 to begin with. We can obviously add more terms. Now, this particular form has to be substituted back in here in the above in this equation, and once we do that, I will sort of avoid or probably fast forward to the separable form. What is going to happen? The most important thing is your radial solution for in the radial coordinates. Now, you know, this is not as simple as your x and y coordinates, because you will probably get this kind of a thing. This is called your Bessel's equation, very famous equation that appears in almost all physical problems, like I mentioned a while back, when we solve things in cylindrical polar coordinates or circular, you know, polar coordinates. So, here in this case we will get k naught square, of course, and kz square, which is nothing but your z dash dash divided by z. We will see that soon, and m square is arising when we do the separation in the theta direction. So, this is like this is multiplied. Now, this is one equation, and another equation is of course your z dash dash plus kz square is equal to 0, and obviously we have theta dash dash theta plus m square theta 0. We have this kind of a thing. Okay. So, the solution of this, obviously there are different ways to write. Let's begin with the theta case, because that would help us get the solution of Bessel function. So, we have sorted out with our transversal direction, and then z direction is straightforward. So, theta direction, obviously it is trivial to see that this is nothing but your trigonometric function. So, your theta as a function of this thing is C1 into cos of m theta. Now, can you tell me what is m value? That is, m is real, of course, but well, can n be integer? Well, for a circular case, or n can be any real number, or is it confined to be only integer? Well, we have a circular duct, and if we fix our theta system here, when we go back and come around, so theta increases from 0 to 2 pi. So, if we consider any generic theta here, theta naught, so if we go around and come back, theta naught plus 2 pi will be the same. So, basically what I am trying to say is that pressure, this will be the same thing. Okay. So, what that would mean is that m must be an integer, otherwise this condition will not be satisfied. You know, it's pretty straightforward. If let us say, if there is no variation, m is 0, then that is about it. Well, you know, you are just getting unity, but when m is 1, you can easily verify cos theta and cos of theta plus 2 pi they are the same. Same thing with m is equal to 2, 3, 4, and the same arguments will hold for the sine function. But if you try it for any other integer, maybe try 1 by 4, 0.3 or whatever it is, half, you will probably not see that. This is fairly straightforward to figure out. Because of periodicity requirement, m must be an integer. There are actually cases when you have a semicircular duct, semicircular muffler, or you have problems in applied physics where you applied maths and all that, where you have wave propagation in a pi kind of a sector, or it is like a vibrating diaphragm of a pi kind of a shape. Then of course, you need to worry about rigid velocity at fixed, this at theta is equal to 0 and this is theta is equal to theta naught. Then of course, m need not be an integer, but for our circular case, perfectly circular duct where there is no partition or there is no restriction to the wave propagation along the circumferential direction, angular direction, then m has to be an integer. It cannot be anything else. Otherwise, there might be a non-integer discrete values based on the boundary conditions along the angular direction. Right now, there is no boundary condition along the radial direction except for periodicity. So, I will write it in bold, periodicity in theta direction. Okay. So, m is integer. Another way, well, this is, you can write this in also in different way, which is basically your, let me call it C into E minus j m theta plus C4 into E j m theta, something like that you can sort of write. Okay. So, theta is, it can sort of vary like this. So, we should be happy with m, and now that is why let me write down your Bessel's equation again. So, this is a vast topic. M I am writing as a suffix here because we are trying to solve for m, and this is a vast topic which arose at least a century back from the time of Bessel, more than a century back I would say. So, here this is like this, we will worry about kz later where m now is an integer. So, this is R m, this is 0. Okay. This is your Bessel's equation. What do you do for solving it? Notice the difference when you had, let us say m is 0, then of course, this term is not there, and but you still have a different term, I mean an additional term, that is your this term. It decays. Clearly, this is like a damping or gradual decrease if you go along the radial direction, and other terms appear to be familiar to your regular sort of wave equation or Helmholtz equation in Cartesian coordinates. So, this is the term that makes it probably quite difficult to solve it, and of course, when you have this term m square by r square, then of course, additional difficulties arise. So, there are several books written on Bessel function. One of the very classical books important books on Bessel function is Treatise on Bessel function, and then lots of engineering mathematics books like Kreyszig or Arfken and Weber, or there are a number of such important texts which talk about, give a detailed account or development of Bessel function. So, there are 4 classes, or probably we can sort of begin with this second order equation really. So, you have your 2 solutions and these are called ordinary Bessel functions of integer order m. So, they are given by your like this Kr, where Kr, this guy is your wave number along the r direction. So, you have your duct, just like you had wave direction along the x direction of y, you have your Kr, okay, and r is the radial coordinate. Now, this is your ordinary Bessel function of integer order m. Well, because m is an integer and this is a second order differential equation, we must also have another solution just like cos sine. So, such a function is called Neumann function. Okay. Neumann function. What is the speciality about these functions? Well, like I said, obviously we are definitely not going to digress into talking about in detail about the properties and or proving the properties or the functions, or proving any identities for that matter. Our job here is to just talk about perhaps the most salient or most important property. One of that is the ordinary Bessel function. This is called, or the first kind, ordinary Bessel function of integer order of the first kind, okay, and this is finite at the origin where m is equal to 0, that is the 0 order ordinary Bessel function of the first kind, that is unity at the origin, and it basically MATLAB has inbuilt algorithms to compute this. Prior to that, people had to really look up tables before cheap computing power was available, and then there have been a lot of asymptotic developments in formulas for such things. And also this actually, there is a series solution that you could do. It is a Frobenius series solution that one can obtain for a general order m, and it can be shown when m is an integer. These two things are Neumann function and these things are linearly independent, and otherwise if m is a non-integer, then it will be like j m or j minus m or something like that. But we will probably worry about these things only, and the plot of that will, for m 0 order, will look like this decaying thing. But if you have m is not equal to 0, 1, 2, 3, 4, it will always start at the origin. So, it will be decaying further and then going like this and something like that. So, this always is finite at the origin, Bessel function of 0 order. Now, what about the n thing? This is called a Neumann function or the Bessel function or the second kind, named after the person Neumann who first proposed the series solution for this. So, this is also called the Bessel function, ordinary Bessel function of the second kind. And what is the peculiarity or special feature of this? This is not finite at the origin, this is infinite at the origin. So, now if you have a problem, often you have mufflers where you have an annular propagation area. Let me just draw it for you. Suppose you have a rigid pass tube, it is called a rigid pass tube, and you have a muffler like this, and say you have a inlet like this and outlet like this. So, if you were to visualize these things like this, and the idea is that only this particular area where I am shading, only that is available, this area is not available for wave propagation. So, under such a case where the origin is excluded from the wave propagation domain, there you have to include your Neumann function, because then there are two boundary conditions. One is a rigid boundary condition, well, at r is equal to the outer radius r naught or r o, and here at also at r 1. But in cases where the origin is included, then you are left with no choice but to drop Neumann function altogether. The full solution, the complete modal solution will be of the form r by r is equal to a times j m k r r plus b times n m k r r. Now, because the origin is included, this is infinite, this is going to 0. So, a times this thing. So, what does the final solution then look like? And of course, we need to apply the rigid wall boundary condition. So, how does that happen? Now, we can again use your Euler equation. So, this is your this thing and your minus p r times r. So, when you put this solution, we will get d of j m k r times r is equal to 0. We will get this rigid wall condition. So, there are roots of the derivative of the roots k r of this equation, or the solution of this equation is basically the roots of the derivative of the ordinary Bessel function of order m. And eventually, just like you have m is equal to, we saw for a rectangular duct that k x was n pi by b or m pi by h for a rectangular or a square waveguide. It is much harder to solve that. It is usually solved numerically, this particular equation, and you often see these numerical values at the back of the textbooks on mathematical physics or applied maths, or even in acoustics. One such place where you can find these values is of course the end of the book by Professor Munjal, Acoustics of Ducts and Mufflers, and other engineering applied textbooks. Another place where you can find the detailed development of these documentation of these roots is my upcoming book, where I can show you the website of such a thing. It is on elliptical mufflers, acoustic analysis of a specialized muffler configuration. But in the initial chapters, second chapter of this book, upcoming book, I have documented not only of course the circular waveguide, also elliptical resonance frequencies of elliptical rigid wall elliptical ducts, and which are very useful to evaluate the transmission loss in terms of the analytical formulation. But at the very last of second chapter, I have given a table of this kind where m is your order and n is the root number because I'll let me try to explain this thing a little more in detail. So, m is your order 0, 1, 2, 3 and so on, and n is your root number. Generally you start with 1, but in this case we will begin with, to maintain consistency with rectangular waveguide, we will call this 0th root, first root, second root, third root, and so on. Now, for this particular equation, this guy, for if we fix m is equal to 0. So, if we have derivative of the 0th order Bessel function, what are we going to get? So, I just briefly discussed the variation of the Bessel function of 0th order, right. Derivative of that would actually start from 0. So, it will be like something like this. You will always find the first root of the derivative of 0th order Bessel function starting from origin, or r is equal to 0. So, that is why again it's consistent with our analysis that for if you set kr is 0 and m of course is 0, then kz will be equal to plus minus k naught, or plane wave mode. So, regardless of whatever shape you deform the rectangular waveguide into, you will always the plane, and if you do not line it with any materials or this is rigid wall thing, then of course your plane wave will always be there if there is no dissipation involved. Now, of course, if you go up, you have your first root here, here, here. These are all your radial modes. So, this is of course, let me write it 0, you will get some this value, I think it is probably about 3.83 and so on. Like this you keep this, then the second root, that is your where the purple curve intersects the y axis here, is 7.05 or something like this, do not remember. Similarly, instead of 0, if you have 1, this guy will start from origin, but you will not consider that root, that will be a trivial solution. So, you will find out the first derivative is somewhere here. So, you will get this first value is 1.84 or something like this, but then there will be sequence of such values, because just like you have m pi by b, where m can be anything 0, 1, 2, 3, any integer, it can be in 10,000. So, similarly, derivative of the Bessel function, if you fix r is equal to r naught, so there are infinite number of roots. So, basically this 3.83 means kr at r is equal to r naught, that is 3.83. So, basically if you put if you put j naught at derivative of Bessel function evaluated at r, k naught r is equal to whatever 3.83, that will be 0. So, this is a non-dimensional value, k naught r is equal to 3.83, where the derivative of the Bessel function goes to 0. So, such formulae or such tables are very nicely explained or documented in a lot of books, and I have also included as a special degenerate case of an ellipse. Elliptical solution is it's quite formidable, and it requires much more detailed consideration. It is a topic in itself. So, we will not be covering that in the course, it is just a brief mention that I made, and those tables of the resonance frequencies of rigid walled elliptical waveguide and also clamped elliptical membranes is given in my upcoming book. So, the interested reader can read that, and so the final solution then will look like the following, where p r theta z is given by your nothing but this double summation from m is equal to 0 to infinity, and your n is also equal to 0 to infinity. We are using a certain convention. Here we have your j m k r m n into r into your we can write this as E j m theta, because it does not matter whether the waves go like this or like this, it is axis symmetric. So, we can just, instead of writing cos m theta or sin m theta, we can probably do with E j m theta or E minus j m theta, and this will be multiplied with your C 1 m n e to the power minus j k z m n z plus C2mn Z, and this will be Ej omega t. So, now this is what we are going to get. Now, Kr of course is fixed by the rigid wall condition. So, this is your solution in rigid wall thing. Incidentally, this is also a solution for soft wall waveguide, but in that case the Bessel function will be evaluated to 0 at the radius r naught instead of the derivative, but for most practical purposes all waveguides are rigid in nature. So, we have your only this condition, like let me write it down again for you, evaluated at r is equal to 0. So, this will give us infinite number of roots for a given order, and we need to consider only the first few based on the convergence. How much is a solution converging? Of course, at higher frequencies more number of roots have to be considered, because the waves become, even the higher order mode starts getting propagating parts instead of being evanescent. They also contribute in the modal summation. So, this is the modal summation solution, and Kr is given by the tables. It's we already know from this condition. So, what is Kz then? Kz is nothing but K naught square minus Kr square. Okay. So, for mnth mode it is given by, clearly the rectangular waveguide was a simpler thing to consider because of the associated thing that because of cos and sine functions. Here we have Bessel functions, that is the only difference, but the life is quite formidable in case of this. So, clearly the k mnth mode will propagate only when k naught is greater than your Kr mn, otherwise it will not propagate. So, what is the one question that arises in our mind is that for a circular waveguide we can probably like to know some numerical value or some handy expression instead of just being quite abstract. So, the as it turns out, like I mentioned in this preceding table, that this is the lowest value. So, basically what it means is that the first mode is the circumferential mode, like your with variation like this. So, this is your corresponding to J1 Kr 1 0 into R. So, what is that value Kr 1 0 into R naught is equal to 1.8412, something like that. Okay. So, at that value we can figure out, that is the cut-on frequency. Basically your K naught R, when it is equal to 1.8412 approx, because when K naught R is equal to K, you have to multiply this by both by R. So, when K naught is equal to Kr, then it is that particular mnth mode begins propagating. So, because we have non-dimensional values, you multiply both sides by R, and we know the value of Kr mn into R, which is 1.84 for 10 mode. So, K naught R is your this particular thing. Now, this is nothing but lambda into R naught is equal to 1.8412. Okay. Now, we probably can do the algebra. 2 R naught is diameter, and your what it will give us is that wavelength should be greater than pi by 1.84 times d, which is equivalent to saying that frequency should be less than 1.84 times pi by d times C naught, or I am sorry, or basically your cut-on frequency Fc is 0.5, if you just 1.84 by pi, if you do, you will get that is 0.5857 times C naught by d. We will sort of get that, okay, we will get that. So, now the thing is that we might be interested in knowing that how do the wave things, how do they look like. So, for that I will directly get on with the book by Professor Munjal. It's given in here. So, we see that it's the planar wave that is the 00 mode, that is Kr00, and this is your spatial variation of the acoustic pressure field across the circular cross section of the duct. So, each half is an opposite phase to the other half, plus minus. So, like this we have alternating minus plus minus plus, here we have plus minus plus minus plus. So, these modes are they are called axisymmetric modes, also known as the radial modes, where I am pointing in this direction, So, they have no theta dependence, they only vary or they show variation only along the radial direction. So, whatever angle you go, you have the same pressure value, but if you vary, if you go along a particular circle, you have 0 variation, and these dotted lines are the nodes. So, along that these are called pressure nodal circles. So, at this value at this radius, pressure is identically 0 and they are alternating phases. So, similarly here we have two nodal circles. On the other hand, these modes along the row are called circumferential modes. So, it is not like they do not have variation along the r direction, but they are regions or lines of demarcation which divide the circular region in the regions of opposite phases. So, here you have basically your Jm Kr10 into r and multiplied by cos theta. So, you definitely have variation along the r direction, but then your angular direction has also variation. So, there is no nodal circle, there is only they are called nodal radii or nodal diameters, which divide the circular region into regions of alternating phase. Similarly, here you have cos 2 theta, that is J2 second order Bessel function multiplied by cos 2 theta. So, it divides into regions of opposite or quadrants of alternating phases. Like this we can have circumferential modes along the r direction, and these are where I am highlighting, these are your cross modes. So, your radial and this variation are both here. So, like this we can sort of analyze the wave propagation in a circular duct stationary medium, and the modal solution is something that I have already sort of talked about, and the cut on frequencies I have also discussed. But obviously requiring all these things, computing all these things using modal solution, I mean incorporating higher order modes, will require access to computer, basically some computing system, MATLAB or Fortran or some programming language, so that you can get the modal solutions. And there are a lot of interesting muffler configurations. We will begin to talk about that from the end of the middle of week 4, where you talk about sudden area discontinuities or extended inlet and outlet. There you have such an axisymmetric configuration. So, all these things, especially the Neumann function things, will be very useful, but we will not do that in the week 4. We will probably try to do one of those cases in the later parts or the end part of the course. But for now, I guess it is time that I stop this consolidated set of lectures for 3D analysis. This was just an introduction to the more important topics that we will be covering. So, as usual, like I mentioned, we will be beginning only from the lumped system analysis, going to the planar wave propagation, talking about transfer matrix using planar waves and number of important muffler elements, how do you quantify the muffler performance and so on, and then talk about perforates. And it is only towards the end that we will sort of begin to use this as a glimpse to the more important things. So, with this I will sort of stop this lectures 3 to 5 of week 2, and I will see you in week 3, where we will talk about all this electroacoustic circuits, lumped system analysis and all that I talked about. So, thanks a lot.